start working with our customer in order to change the behavior, in order to prepare the sustainability. The second part is when we do the modelization, we can compress the intervention. We can compress a lot of visit, and we can do very fast. We are 64 times faster than any classical design office. So we can gain a lot of time and a lot of carbon. The maintenance predictive with the digital shadow can allow us to make alerting in real time. And the last part, if we can do the mixed reality intervention and the remote maintenance, then we can perhaps get this zero carbon for the tower co-process. Here, shortly, I can show you the limitation that we are facing with our customer. The first limitation is the data, because the data is the first. We cannot do modelization, even if we are very strong and very advanced in technology. If we haven't available data and we haven't accurate data, we cannot do. And this is the first challenge. The second challenge is how to make with this beam and 3D structural model and repository in order to know the color of our asset or of all our building in real time, because today this is a big challenge for the TowerCo. The second one, it's time, because to make a design today, for example, if we want in every, for example, here to make a deployment of 5G or 6G tomorrow, we have to make a lot of time to make the design and a lot of time to make the conception and to go to the work and to make the realization of the project. And the time is a few months. So the third challenge is the maintenance, because TowerCo, they are making a lot of budget, 200 million euro for the maintenance for the asset every year. It's a big, and the supply chain with the problem of the availability of the steel, for example, there are a lot of problems, and then we have a lot of issue in the profitability. So what we propose to our customer is this solution. So we start with doing IA and audit of the data of the TowerCo. We see if we have all data or not, if we have accurate data or not, if everything is available to make the modelization. And we did, our machine can do a lot of documentary audit in order to make data accurate. The second part is the beam. We generate two modelization. The first modelization is the modelization with 3D structural. Does mean that we can make the effort on the battlement or in the building, and we can make if the building it's robust, in order to make any other update or modification in the building. Because when I go from 4G to 5G, I have to change the equipment, so I will change the effort. And then we did the beam. The beam is the cover, and it's the information that we put in the 3D structural model in order to make the design in real time and very faster. And we can compress the design from several months to few minutes to get the design. This is the strong point, is rapidity of the beam with Arya Towers. The third part is the digitalizable supply chain. Does mean that we are putting with our machine, and I will explain this, with our machine that we can use, we normalize the reinforcement kit, because the design can be okay to make the deployment or not okay, and then we should make a reinforcement in the structure. So the reinforcement nowadays is personalized. So what we are proposing, it's a norm or a standard reinforcement kit that is calculated with the machine, our machine Arya Towers, and can be proposed to our customer in order to go very fast and gain 75% of time of conception and reinforcement, and 80% of carbon and 70% of cost. The last two parts is the digital shadow, it's the maintenance, and the remote maintenance with the augmented reality that make a stream in the two sense from our platform to the OT operational technology platform of the customer. And I can show you here our performance. So this is the classical process for any tower co. They take a lot of months in order to, from the beginning of the project until they go to new technology, for example, or any reinforcement, they take all this time. With Arya Towers today, we take only 3 weeks. So we are in real time with the beam process 4.0. And I can invite you in our booth Friday in the afternoon. We will make demonstration of how we use the beam process in order to accelerate the design generation. And the supply chain is done in 2 days. And then you can make the project, you can finalize it in very, very fast method. Here, this is the demonstration that we did with the POC of our tools that we can do reinforcement, we can use the reinforcement. Does mean that nowadays, to make any reinforcement, we have to make a conception, then we make the production, then we mount the kit in the tower, and then we can validate the reinforcement. For this, our tool, we can reuse any kit from nearest tower. For example, let's take this example. For this tower, we need to reinforce with the 3 meters because we need to put a new equipment. So we need 3 meters of reinforcement. The tool can find that there are another tower that have available kit that we can reuse. So when I reuse the kit, I will gain 30,000 euro and I will gain 1,300 or 400 kilogram of carbon, and I can be faster than when I make a new kit and I construct a new kit. This machine as developed by Arya Towers after the beam modelization. And by the last slide, I can show you some of our performance. So our solution are used 80% from actors in tower French market. Here in France, we have 60,000 tower, and Europe we have 1 million tower. So our solution are used now in market, and this is the unfair performance. So you see that our customer, you know, the color is SFR. By the January 2022, they were the first, for the first time in history, in the deployment 5G. They become the first before Orange and Bouygues and Free for the first time because they make the design with the beam model and they are very, very faster, and they have their SFR, they have their color of the set all around France. So you can see that you can see in real time the capacity of each tower, and this is the realization of our beam or our 3D structural model, and this is what make the design very fast and very easy to do. This is what I try to share with you, and I thank you very much for your attention. And if you have any question, I'm here, and I invite you Friday in afternoon to our demonstration. Thank you.
Thank you, Maher, and we look forward Friday to see some demonstrations and to claim on the tower to see how your AR is working there. Good. So now we have to split. So you have 2 options. Menu A is stay here in the room and follow the tutorial. Let me also present that. Yeah, maybe we can change.
Okay. Anyway, you have it on your own. So I'm looking at the program. So now you have the choice between staying here and following the tutorial, which is called the use of deep learning algorithms in geometry, or go in the room H218. We will indicate how to reach that room, and follow the first part of an workshop on environmental and sanitary impacts of the metaverse. That workshop has two parts. The first part before the coffee break and the second part later on. Of course, both the tutorial and workshop are also online, so you can also connect with the other one while you are here. So let me initiate the one that will continue in these themes. Let me just check with Athanasios if you can hear me. Great. Can you try to share your screen? No, you can hear me. Athanasios, you can hear me? Can you confirm? Yeah, they can hear me. Okay, but now you can try to share your screen just to make sure that we can see your screen. No one wants to go with that? That's fine. There will be two.
Okay, another test. Oh, great, great. Okay, good, and we have you on the screen. So can you try, please, to share your screen? Ziad, just stay 2 minutes. Just stay 2 minutes to make sure that Athanasios can share the screen. So you have to give him the possibility to share the screen and also to have the microphone. Athanasios. Yes. Okay, try now, Athanasios.
Good afternoon.
Yeah, we can hear you.
Okay, I can share, but also a co-author, a colleague that we are going to present together should be you should have the ability to share screen and speak in the microphone.
Okay,
Yeah.
and is Chrysoula. Yeah.
Yeah. Yes. Yes.
Can you also activate Chrysoula for the same permissions? So share the screen and microphone. Yeah, it looks to be okay for us.
Okay, now. Okay.
Good. The floor is yours.
Okay, so we will start with a short introduction to the tutorial. Then we will share a video we have already prepared with a presentation. And finally, we will go on with some, let's say, workshop and some hands-on experience on the stuff that we are going to present during the tutorial. I mean, deep learning and implementation to graphics. So finally, we're going to have live presentation, and we will end, of course, with questions and any discussion in the end. Okay. So first of all, about our tutorial. In this tutorial, we deal with the requirements of Web3D models, and particular X3D formatted models, in order to work efficiently with deep learning algorithms. The reason we're focusing in this particular type of 3D model is that we consider Web3D as part of the future in computer graphics. The introduction of metaverse technology indeed confirms that lightweight 3D models will be an essential part of many novel services in the near future. Furthermore, X3D language is expressing 3D information in a way semantically friendly and so very useful for future applications. In our research, we conclude that the lightweight X3D models require some vertex enhancement in order to cooperate with deep learning algorithms, and we suggest algorithms that may be applied and make the whole process in real time, which is very important in case of web applications. Machine learning classification is a rather mature research area that gains more and more attention during the last decade, especially after the introduction of deep learning technology. The use of deep learning algorithm in geometry classification has also gained some serious attention, since it is related to the classification and finally recognition on geometries of objects that are either synthetic, which are usually meshes, or created by cameras in the case of photogrammetry or laser scanners, which are usually producing point clouds. So we will start the tutorial from the basic introduction of deep learning algorithms, and we will finish with a demo implementation of a point cloud classification algorithm. In our experiment, we tested, as you will see, training and testing with mixed kind of models, like, for example, training with point clouds and testing with meshes, and also testing with models found outside of the official datasets, models that we can find, freely in the internet, all around the internet. The results are very encouraging, I may say, and easily we may achieve positive predictions of up to 80% or even more. Now, what's the real motivation? The real motivation, as we said, it is, of course, to enhance X3D and Web3D with the capability to work with deep learning algorithms, which is very crucial for the future. Also, we see and we predict and we envision, we may say, applications that will provide us with new services in the near future. We have, for example, autonomous cars. We have autonomous devices and machines working in factory environments, etc. All these can benefit by algorithms that using deep learning in order to recognize their environment. Also, there are many applications that we expect we are going to see in the near future that will use classification and even more segmentation of 3D scanning environments. Scanning of the real environment, producing the 3D model is rather, let's say, something easy to do right now. You can do it with laser scanners. You can do it with cameras, even more. So we expect that in the near future, most of the machines, most of the cars, most of the devices, they are going to embed systems that will produce virtual environments, 3D modeling out of video or laser scanning, and so classification and annotation of all these models will be very interesting. Now I will share the video through the screen, okay, and in the end we are going to have the hands-on workshop. Okay. Just tell me if you can see the video, but the question is if you will hear the sound. I'm not sure if I can do that. Sorry.
Yeah, it was visible, but just play for 1 second to see if we have the audio.
No. I'm trying to share the video here. The question is how I will share the sound of the video, not the video itself.
Only the sound or video and sound?
Video and the sound, I mean, yeah.
I think it will go through. Just play it to see. If you hear, maybe we will hear.
This is the old-time classic way, but I suppose that there is some kind of, okay, I do. I can see it. I can see it. I think now you will hear it. Huh? You hear it?
No, we only have the video data, or I cannot hear it. No. But okay. you can hear. Okay, go on.
So you hear me? You can hear. Okay, I'll tell you what. I will try it again. Okay. I assume that you hear me.
Yeah, we can hear you. Your voice.
Include system audio. Okay. And this one. So you should hear now. Music.
Good morning everyone. Thank you for participating in our tutorial. This is a pre-recorded video, so hold your questions till the end for the Q&A part. In this tutorial, we will discuss about the use of deep learning algorithms in geometries. We will mention some useful tools and techniques for data processing. Also, we will discuss about neural networks and their applications in 3D meshes. So, let's start with the artificial intelligence structure. As you can see, neural networks form the base of deep learning. Deep learning is a subfield of machine learning where the algorithms are inspired by the structure of human brain. So, artificial intelligence refers to the idea of giving machines or software the ability to make its own decisions based on predefined rules or pattern recognition models. The idea of pattern recognition models leads to machine learning models, and deep learning is a machine learning technique that teaches computers to learn by example. There are two more definitions that I'd like to mention. As you can see in this figure, data mining is a combination of machine learning and AI. So, data mining is the process of finding anomalies, patterns, and correlations within large datasets to predict outcomes. Big data is large, more complex datasets, especially from new data sources. These datasets are so voluminous that traditional data processing software just can't manage them. But these massive volumes of data can be used to address business problems you won't have been able to tackle before. Machine learning is a way that we teach computers to learn about the world by looking at patterns or examples of things. A machine looks at information like a human being, but it is kind of more like a collective memories that a person memorizes. So, in order to build a machine learning system, we need to train it with a collection of data. Machine learning algorithms build a model based on sample data. That's our training data, in order to make predictions or decisions without being explicitly programmed to do so. So here we have two different classes. The first one contains 5 different chairs and the second one contains 4 different tables. The last photo shows an unlabeled furniture. Most of you may think that this is a chair because your mind combined this picture with the last picture of the chairs in our class. But what if I tell you that this is a table? Now your mind is trying to detect some general features that will confirm my theory. That's how a machine learning model works. Machines looks at information like a human being. When you learn a new subject or a new skill, the neurons in your brain form new connections with other neurons. The more you study or practice, the stronger these connections become. Neural networks are here to simulate the way that human neurons works. The figure on top is the simplest version of a non-deep neural network. As you can see, it is divided into 3 layers. The first one is the input layer that collects all the information from the sensors of the outside world. The hidden layer is here to process all the collected info. And then we have the output layer to help us release the processed information to the outside world. In general, I want you to imagine that a neural network is like a curious toddler. His eyes and ears are the sensors that help him to collect the info from the outside world. That's the input layer. The hidden layer is his brain and helps him to process all the information he received from the input layer. And the output layer is his mouth. The first figure here is a simple version of a deep neural network. Again, it has an input layer, a hidden layer, and an output layer. All the information are going from the input layer to the hidden layer and then to the output layer. The first figure shows the simplest version of a deep neural network. The primary difference between a deep and a non-deep neural network is the number of columns in the hidden layer. A non-deep neural network has only one column in the hidden layer. A deep neural network has more than 2 columns in the hidden layer. The circles in the structures are called neurons. The input neurons hold the input data and they pass this info to the hidden layer neurons. The hidden layer neurons are applying weights to the data they receive, and the output layer neurons are responsible for sending the processed data to the outside world. A weight shows the importance of a neuron. For example, if the weight from node 1 to node 2 has greater magnitude, it means that neuron 1 has greater influence from neuron 2. Assuming that x is the input information, the multiplication of x with the weight w is the output of a hidden layer neuron. So if we have two more inputs, each one of them will be multiplied by a weight in the hidden layer. Also, another parameter that is added in the hidden layer is bias. Bias allows you to shift the activation function by adding a constant to the input. This is like an extra weight. Weights are showing us the strength of the connection and the amount of influence a change in the input will have upon the output. Bias represent how far off the predictions are from their intended values and shows the differences between the function's output and its intended output. Both of them are adjusted towards the desired value and the correct output and receive random values. In artificial neurons, inputs and weights are given from which the weighted sum of input is calculated, and then it is given to an activation function that converts it into the output. So basically, an activation function is used to map the input to the output. It is a very important feature of artificial neural network, basically decides whether a neuron should be activated or not. This means that it will decide whether the neuron's input to the network is important or not in the process of predicting using simple mathematical operations. Sigmoid is the most used activation function with ReLU and TAN. Sigmoid is a nonlinear activation function, also called logistic function. Nonlinear means that output cannot be generated from a linear combination of inputs. If we use linear activation function in a deep neural network, no matter how deep our network is, it will be equivalent to just a linear neural network with no hidden layers, because those linear activation functions can be combined to form another single linear function. So basically, our whole network will be reduced to a single neuron with that combined linear function as its activation function, and that single network won't be able to learn complex relationships in data. Before we analyze the training methods, it's important to define the loss function. This function evaluates our neural network for a certain task. Basically, it shows the relation of the desired output and the output we actually receive. So, M value refers to the number of testing samples, Y values is the labels we wish to receive, and Y hat is the labels we actually received after testing our neural network. So, in our example, we have two pictures of chairs and two pictures of tables. The Y value for chairs has the number 0, and the Y value for tables has the number 1. Each time we run our neural network, we wish to receive 0 for chairs and 1 for tables. Thus, the loss function is considering how many bad guesses we had, so the output value of the loss function must be as small as possible. Now, it's important to define the learning rate and the epoch. The learning rate value should be small, often between 0 and 1, because we want to train neural network in small steps, keeping loss function to small values if possible. Learning rate is a positive number that further determines the frequency we update the weights in the hidden layer of the network. For instance, if the learning rate value is too small, the weights are updating slowly, so the training has slow progress. A peak learning rate means that you roughly search for the best area in the space. A suggested number could be around 0.1 or 0.01. That means we apply weights 0.1 or 0.01 to the parameters. An epoch is a machine learning term that refers to how many passes the machine learning algorithm has made across the full training dataset. Batches are commonly used to organize data collections, especially when the amount of data is very large. The number of epochs equals the number of interactions if the batch size is the whole training dataset. In the construction of various models, several epochs are employed. For example, when the dataset size is D, the number of epochs is E, the number of interactions is I, and the batch size is B. There are many algorithms whose applications aim to adjust the values of the weights of an artificial neural network. Learning methods can be classified into two categories: supervised learning and unsupervised learning. The use of labeled data distinguishes supervised learning as a machine learning technique. These datasets are used to train or supervise algorithms so that they can effectively identify data and forecast outcomes. The model can track its accuracy and learning rate over time by using labeled inputs and outputs. Also, supervised algorithms are using the knowledge of labeled datasets to try to generalize the new examples that it's never seen before. Supervised learning is divided into two more categories: structural learning and temporal learning. The included unsupervised learning algorithms are called self-organized, and they are procedures that do not require an external teacher or supervisor to be presented. Unsupervised learning analyzes and clusters unlabeled datasets using machine learning methods. These algorithms uncover hidden patterns in data. Some examples that represent unsupervised learning include the Hedian algorithm and the min-max algorithm. The most famous deep neural networks are the convolutional, which are commonly used to process 2D data, such as images. These networks work by directly extracting features from data, a method that automatically makes models accurate for tasks of computer vision. Their architecture is simple and includes one input layer, many hidden layers with ReLU activation function, and an output layer. Artificial neural networks are consisting of collections of artificial neurons inspired by the biological neural networks of human brain. Multi-layer perceptron is a type of feed-forward artificial neural network. It refers to many networks built of many layers of perceptrons in some cases, and any feed-forward artificial neural network in others. Feed-forward neural networks are types of artificial neural networks where the connection of their nodes do not form any loop, and their exact opposite are recurrent neural networks where connections between nodes can create a circle. In classification, all objects in a single image is grouped or categorized into a single class. So, when we talk about classification, we ask the question, what type of object is this? And the goal is to classify the entire point cloud or object with one label. While in segmentation, each object of a single class in an image is highlighted by different shades to make them recognizable to computer vision. In segmentation, we ask the question, can you separate this object into distinguished parts? The key idea here is to group object into tiny pockets based on a specific characteristic, like for example the distance. So, here is an example. If we have a picture of a chair, in classification we will apply the label chair to the whole image. In segmentation, we will apply one label to define the seat, one to mark the chair legs, and one for the back. This process is called part segmentation. Also, we have semantic segmentation. Its application can be seen in an image of a traffic road, where we want to apply one label for people, one label for cars, and one label for traffic lights. Before we move on, I'd like to show you some useful algorithms that may help you increase the performance of your network. Max pooling is a sample-based discretization process. The objective is to downsample an input representation. It aims to reduce overfitting by offering a simplified version of a representation. It also minimizes the computational cost by lowering the number of parameters in the learning process, as well as providing basic transformation invariance to the internal representation. Normalization is the process of transforming data into a scale that is consistent across the dimensions. The most common technique to achieve this is to split the data by the standard deviation of each dimension. It makes sense only if you have reason to suppose that distinct input features have different scales, yet all equally important to the learning process. Normalization gives equal weights importance to each variable so that no single variable steers model's performance in one direction just because they are bigger numbers. Triangle point picking is a very useful method. It helps us to fill the area of a triangle with points. So, given a triangle with one vertex at the origin and the other at positions v1 and v2, one might think that a random point inside the triangle would be given by the function you can see. You can see the output of this function in the first image. However, as you can see in the first plot, this samples the triangle non-uniformly, concentrating points in V1 corner. Randomly picking each of the triangle's coordinates from the union distribution 0 to 1 also does not produce a uniform point spacing on the triangle. As you can see in the second plot, the resulting points are concentrated towards the center. To pick points uniformly distributed inside the triangle, you can use the multiplication of V1 with A1 and A2 with V2. As we said before, A1 and A2 are uniform variables in the interval 0 to 1. V1 and V2 are the positions of two other vertices. On the last image, you can see a representation of a sofa before and after the triangle point picking method. K-nearest neighbors is a supervised machine learning algorithm. It can be used to solve both classification and regression problem statements. The number of nearest neighbors to a new unknown variable that has to be predicted or classified is denoted by the symbol K. As you can see in our figure, first we have 4 yellow dots and 3 gray dots. The white dot on the center must be classified in a category. So, if we set k value equal to 5, this means that the algorithm would look for the 5 nearest neighbors. As you can see, the nearest neighbor in the white value are 2 black dots and 3 yellow dots. So, the white dot will be yellow because 3 of the 5 nearest neighbors of white dot are yellow. In order to find the nearest neighbors, we must calculate the distance between points. There are many ways to calculate the distance between points. The most common one is the Euclidean distance. Euclidean distance between 2 points in Euclidean space is the length of the line segment between 2 points. It can be calculated from the Cartesian coordinates of the points using the Pythagorean theorem, therefore occasionally being called the Pythagorean distance. Manhattan distance, also called taxicab distance or the city block distance, calculates the distance between two real-valued vectors. It is perhaps more useful to vectors that describe objects on a uniform grid, like a chessboard or a city block. As you can see in our plot, Euclidean distance goes from A to B by calculating the distance z, while Manhattan distance goes from A to B by calculating the x plus y. So, let's see what happens if we want our models to learn something that has more than 3 dimensions. The inductive bias, also known as learning bias of a learning algorithm, is the set of assumptions that the learner uses to predict outputs of given inputs that is not encountered. In machine learning, the term inductive bias refers to a set of assumptions made by a learning algorithm in order to perform induction, that is, to generalize a finite set of observations, training data, into a general model of the domain. Generally, every building block and every brief that we make about the data is a form of inductive bias. Inductive bias play an important role in the ability of machine learning models to generalize to the unseen data. For example, in the case of rotation symmetry, inductive bias could be perhaps as the assumption any information that is not invariant under rotations can be and should be ignored. The sample's density increases with the increase of the dimensionality. When we keep adding features without increasing the number of training samples as well, the dimensionality of the feature space grows and becomes sparser and sparser. The dimensionality reduction refers to the transformation of data from the higher dimensional space into a lower dimensional space so that the lower dimensional representation retains some meaningful properties from the original data. Two more important definitions are Euclidean and non-Euclidean data. Non-Euclidean data refers to a set of data points which do not fit into two-dimensional space. Euclidean is the exact opposite. In Euclidean, data are certainly modeled as being plotted in n-dimensional linear space. For example, image files. So, Euclidean geometry seeks to understand the geometry of flat two-dimensional space. And from the other hand, non-Euclidean geometries studies curves rather than flat surfaces. In this point, I would like to show you some geometric deep learning models. A convolutional neural network, also known as CNN or ConvNet, is a class of neural networks that specializes in processing data that has a grid-like topology, such as images. A CNN typically has three layers: a convolutional layer, a pooling layer, and a fully connected layer. The term fully connected layers, also known as linear layers, connect every input neuron to every output neuron and are commonly used in neural networks. A CNN is a classifier because it's used to recognize patterns in data. So, CNN refers to multiplying the input neurons with a set of weights that are commonly known as filters or kernels. As you can see in the pictures, the filters act as a sliding window across the whole image and enable CNNs to learn features from neighboring cells. As you can see in the two pictures, this layer performs a dot product between two matrices, where one matrix is the set of learnable parameters, otherwise known as kernel, and the other matrix is the restricted position of the receptive field. This produces a two-dimensional representation of the image known as an activation map that gives the response of the kernel at its special position of the image. The pooling layer replaces the output of the network at certain locations by deriving a summary statistic of the nearby outputs. This helps by reducing the spatial size of a representation. The pooling operation is processed on every slice of the representation individually. The CNN can now be run on a 3D object itself rather than a 2D image of the object. Analogously to 2D CNNs, the kernel would pass through every pixel represented as node in point cloud, basically a graph that wraps around the 3D object. So, 3D convolution applies a three-dimensional filter to the dataset and the filter moves three directions, x, y, z, to calculate the low-level feature representations. Their output space is a three-dimensional volume space such as cube. Three-dimensional max pooling layer performs downsampling by dividing three-dimensional input into pooling regions. Then it computes the maximum of each region. For 3D image input, the layer pulls over the spatial dimensions. Data with 5 dimensions corresponding with pixels in 3 spatial dimensions, the channels and the observations. For 2D image sequence input, the layers pulls over the spatial and time dimensions. A graph neural network is a class of artificial neural networks for processing data that can be represented as graphs. Also, they learn features by inspecting neighboring nodes. The major difference between CNNs and GNNs is that CNNs are specially built to operate on Euclidean structured data. GNNs are the generalized version of CNNs, and they have unordered nodes. So, there is an application of GNNs in 3D meshes. GNN here considers distance and angle from a point of 3D images or the degree of neighboring nodes on graphs. The position and values of kernels on the neighbor structure are not fixed, but rather learned from the training process. RNNs are classes of artificial neural networks where connection of nodes can create a circle, allowing output from some nodes to affect subsequent input to the same nodes. It is commonly used in speech recognition and natural language processing. So, a representation of the previous inputs is called hidden state. Here, there is an example of recurrent neural networks. Assuming that we have the phrase, "What time is it?" The first word, "what," products an output so that RNN has info about the word "what." The next word, "time," products an output so that RNN has info about this new word, and with the help of the hidden state from the previous step, RNN has info about the words "what" and "time." This process is repeated until the end of the phrase, but RNN remembers more the last produced output. So today we will discuss about two artificial neural networks. Both of them are used to recognize 3D meshes, but with different techniques. PointNet is an innovative, highly efficient net that uses neural networks to detect 3D objects without rendering. It was created by the team of Stanford University to provide several applications for scene semantic parsing to object classification. The network effectively learns a set of optimization functions that selects critical points in the point cloud and then codes the rationale of their selection. The network's last fully connected layers combine these ideal critical points into a global descriptor to the entire form to achieve safe classification or forecast per point labels for segmentation. Since each point may be transformed individually by a fine transformation, it is required that points to be pre-processed for inserting them to the algorithm. This preprocessing tries to canonicalize the input and makes it independent to potential rotation or transformation of initial model before the PointNet analyzes it. Let's move on to the architecture of PointNet. The whole idea of classification network is to increase input's dimensions. More specifically, the classification network maps each of the endpoints from 3 dimensions to 64 dimensions by using a shared multilayer perceptron. It is critical that each of the endpoints has its own multilayer perceptron. Similarly, each endpoint is transformed from 64 dimensions to 124 dimensions in the following layer. A max pooling is further used to construct a global feature vector. Finally, the global feature vector is mapped to k-output classification scores using a 3-layer fully connected network. PointNet employs max pooling. The output of max pooling compresses the endpoints in the input point cloud to a subset of points, similar to how the max operator compresses numerous real-valued inputs to a single value. The critical point set is made up of points that contribute to and define the global feature vector. The global feature vector may be used to derive the significant amount of intuition. To begin as previously started, the dimensionality of the vector refers to as the bottleneck dimension, and it is directly related to the expressiveness of the model. More intriguingly, the network learns to summarize the input point cloud using a sparse collection of important points, which closely matches to the skeleton of the objects according to the visualization. A mini-network predicts an affine transformation matrix which we then apply directly to the coordinates of the inputs. Multilayer perceptrons are used to translate the input points to a higher dimensional space independently. Max pooling is employed to encode the global feature vector. The final fully connected layer's input-dependent features are then merged with globally trainable weights and biases to produce a 3x3 transformation matrix. To align features from distinct input point clouds, we may use another alignment network on point features and predict a feature transformation matrix. The transformation matrix in the feature space has a far more larger dimension than the spatial transformation matrix, making optimization much more challenging. As a result, we include the regularization term in the softmax training loss. Softmax is the activation function. Each of the n input points in the segmentation network must be allocated to one of the k segmentation classes. Segmentation relies on both local and global features. The points in the 64-dimension embedded space, which is the local point features, are concatenating with global feature vector to produce a per-point vector. In other words, after computing the global feature vector, the algorithm feeds it back to the point features by concatenating global feature vector with per-point features to get a desired outcome. MLPs are used to the endpoints to reduce the dimensionality. In this figure, you can see the whole architecture of PointNet. A three-dimensional model starts from the classification network, and each time we want to increase dimensionality, we apply a T-net. As we said before, T-net outputs local features and max pooling outputs the global features. These two features are concatenating for each point. Part segmentation is a challenging fine-grained 3D recognition task. Given a three-dimensional scan or a model, the task is to assign part category label to each point or face. Most object categories are labeled with 2 or 5 parts. Ground-truth annotations are labeled on the sampled points on the shapes. Evaluation metric is MIOU on points. So for each part type in category C, they compute MIOU between ground truth and prediction. So MIOU refers to the deviation of the area of overall with the area of union. In order to calculate MIOU for category, they take average of MIOUs for all shapes that category. The 3D CNN segmentation network is simple. For a given point cloud, they first convert it to the volumetric representation as an occupancy grid. Then 5 3D convolutional operations, each with 32 output channels and stride of 1, are sequentially applied to extract features. Finally, a sequence of 3D convolutional layers is applied to the computed feature map to predict the sequential labels for each voxel. ReLU and batch normalization are used for all layers except from the last. Batch normalization is a method used to make training of artificial neural networks faster and more stable through normalization of layers inputs by recentering and rescaling. Let's move on to the MeshNet. MeshNet is a neural network that learns from mesh data directly for 3D representations. To deal with the challenge in mesh data processing, the faces are regarded as the unit and connections between faces sharing common edges are defined. Moreover, the feature of faces is split into spatial and structural features. Based on this idea, they designed a neural network architecture with two blocks named spatial and structural descriptors for learning the initial features and a mesh convolutional block for aggregating neighboring features. In this way, the proposed method is able to solve the complexity and irregularity problem of mesh and to represent 3D shapes well. A list of faces with initial values is fed into two blocks named spatial descriptor and structural descriptor to generate the initial spatial and structural features of faces. The features are then passed through the same convolutional blocks to aggregate neighboring inputs, which get features of two types as input and outputs new features of them. The pooling function is applied for features of all faces for generating global features, which is used for further tasks. There are two key ideas that helped with the architecture of MeshNet. The first one is to regard faces as an only unit and define a connection between two faces if they share a common edge. There are several advantages of this simplification. First is that one triangle face can connect with no more than 3 faces, which makes the connection regular and easy to use. The second key idea is to split features of faces. We only need to know the position of the point and the look of a face. These two key ideas help to transform mesh data to list of faces. The initial values of a face are the face information and the neighbor information. The face information contains coordinates from the center point, vectors from the center point to 3 vertices, and the unit normal vector, while the neighbor's information contains indexes of the connected faces. So, the center values are the inputs of the spatial descriptor and the spatial descriptor outputs initial spatial features. The structural descriptor is divided into two categories. The first one is the phase rotation convolution, which captures the inner structure of a phase and focuses on the shape information of phases. The input of this block is the center value. After the rotation convolution, they apply an average pooling and a shared MLP to each phase. In this way, they output features. Another structural descriptor they design is the phase kernel correlation, which aims to capture the outer structure of the phase and explore the environment where the phase is located. In their phase correlation, they select the normal values of each phase and its neighbors as the source. The learnable set of vectors are the reference kernels. Then they calculate the kernel correlation between each phase and kernel, and more similar pairs will get higher values. The mesh convolution block is designed to expand the receptive field of phases, which denotes the number of phases perceived by each phase by aggregating information of neighboring phases. The mesh convolution block contains two parts. The first one is the combination of spatial and structural features, which they use the most common technique of combining two types of features, which concatenates them together and applies MLP. In this pipeline of the network, they concatenate all the combination results of generating global feature. The second part is the aggregation of structural features. With input structural features and neighbor index, they aggregate the features of the phase with features of its connected phases. There are many aggregation methods such as average pooling, max pooling, and concatenation. Average pooling calculates the average values of features in each channel. Max pooling calculates the max value of features in each channel. And concatenation concatenates the features of phases with features of each neighbor representation, passes these pairs through the shared MLP, and applies a max pooling to the results. So let's see some very useful libraries for machine learning and deep learning. TensorFlow is a Python library for fast numerical computing created and released by Google. It's a foundation library that can be used to create deep learning models. By using TensorFlow.js, we can display models on web. Also, TensorFlow Lite is a mobile library for deploying models on mobile microcontrollers and other edge devices. Also, TFX can be used to create and manage a production pipeline. A TFX pipeline is a sequence of components that implement an ML pipeline which is specifically designed for scalable, high-performance machine learning tasks. Keras is a TensorFlow library. So you can export Keras models to JavaScript to run directly in your browser, to TF-Lite to run on iOS or Android, and embedded devices. The homepage of Keras website contains information about the Keras library and how to install Keras in Python. It also contains a guide, Keras API documents, and examples. On the Keras examples document, you can find code examples about computer vision, natural language processing, structured data, time series, audio data, generative deep learning, and graph data. Scikit-learn is a machine learning Python library. It is used to predict data analysis. It contains algorithms for classification, regression, clustering, dimensionality reduction, model selection, and preprocessing. So, let's move on to our application. Our main goal was to train PointNet and use it on a web page for live prediction in X3D meshes. We chose PointNet because we wanted our application to work well with point clouds and 3D meshes. The dataset we used for training is called ModelNet 40. This dataset is created by Princeton University and it contains CAD models from 40 categories. The goal of the Princeton ModelNet project is to provide researchers in computer vision, computer graphics, robotics, and cognitive science with a comprehensive, clean collection of 3D CAD models for objects. On the web page modelnet.cs, web.princeton.edu, you can find ModelNet 40 and ModelNet 10. ModelNet 10 contains CAD models from 10 categories. Here you can see all the Python libraries we used for training and building our model. As you can see, we used Keras, TensorFlow, NumPy, and TensorFlow.js. Each one of them helped us in different situations. In order to build PointNet in Python, we used the implementation from the web page of Keras. TensorFlow.js helped us to save our trained model in a JSON file, and we used NumPy for some simple data processing tasks. When we want to deploy a machine learning model on web, we have two options. Our first option is to train our machine learning model in Python. Our second option is to train our machine learning model in our web page. In our case, we used the first option. So, after training our machine learning model in Python, we used TensorFlow.js to save our trained neural network in an external file. So, in our case, our external file has the name 3500 MyS model, and it contains a JSON file and a bin file. The JSON file, named ModelNet.json, carries the topology and references to the weights, and the binary file carries the weight values. So, if we want to use this model in our web page, we have to write the method TensorFlow load layers model and import the JSON file. And if we want our model to predict something, we have to use the method .predict. The results of this method are integer numbers that correspond to the classes of the objects we used for training. The first view of our web page contains information about this seminar, information about the paper we wrote, and the 4 3D scenes that contains X3D objects and a neural network to predict the objects. In our application, we trained one neural network with 40 classes to be able to predict all the objects from the scenes. Thus, we used the same neural network for all the scenes, but we save it in 4 different files to avoid the confusion of the network in case a user opens more than one scenes at the same time. So, assuming that the user chooses the first scene, on each scene, you can find information about the scene, the X3D scene, and you can create a bounding box to see the network's wrong and right predictions. If you scroll down to our web page, you can find a matrix that contains information about the classification performance after training with 20 epochs and testing with 20 individual objects. 50% of the testing objects are from ModelNet 40, and 50% of them are from the internet. So, if you click in the link below the matrix, you can find the dataset we used for testing, an example of the source code we used to train our neural network in Python and to build our web page. This video is a guide for users. That was all. Thank you so much for participating. We will be happy to answer your questions. Thanks again.
So, I am back. This was just the pre-recorded presentation. As you can see in the chat box, we have a link where you can find, after the end of the tutorial, you can find the video you just saw, as well as the material, I mean the presentation. And right now you can find the experiments we did, as well as the results of the experiments and the data set and the source code of the whole experiment. Okay, so there you may find all the material. Now I'll pass the screen to Chrysa. Chrysa is a colleague here in the Hellenic Mediterranean University, and she will give you some hints on the hands-on hints on how you can do all these experiments by your own. I mean, how you can work with neural networks, with Keras, with TensorFlow, and finally, how you can export the trained neural network in order to use it in your web page with the Web3D material. Okay, so Chrysa, you may share your screen now.
Hello, everyone.
Okay, yeah.
So this is the Python code we used for training and testing our machine learning model. As you can see, we are using Jupyter Notebook. This is an environment that runs Python code. So we used the implementation from the web page of Keras in order to build and train our PointNet, our machine learning model. The first command here, the first cell here, has only all the libraries we used. So we have the OS library, because we wanted to manipulate paths to reach the training data. We have the globe library, because we wanted to, it helps us to return all the file paths that match a specific pattern. The NumPy, which we named it as NP, and it helps us to work with arrays and matrices. The matplotlib library that helps us to visualize our data. And also we have TensorFlow library that helps us to implement the Keras library. As you can see here, we wrote helps us to build our model in layers. So in TensorFlow.keras.layers, we implement the dense, which means that our dense means that our layers are fully connected. So in order to build a model that has fully connected layers, we want this library here. And again, we have the regularizers that allows us to apply penalties on the layer parameters or activity during optimization. And the penalties are summed to the loss function, to the loss value. And then we have the backend. It is the part of the machine learning software that runs the algorithms. And finally, from TensorFlow.keras.initializers, we imported the constant for initialization tasks. Our next step is to import the file name that contains all the data of our training and testing. This model, the name of this file is model B, and it contains 3D objects in no file format. As you can see here, we have the function parse dataset, and we are calling it here. So in order to take the point clouds of the objects on the training and testing dataset, we need to define the number of points that we need for each object. Here is this, and the batch size. Here is 32. So the output of this function is a training array, a testing array, the labels of the training array, and the labels of the testing array. Also, we have the class map that saves and keeps the labels for each class. Here, our dataset contains two classes. As you can see, here is the bathtub class and the sink class. So this is what gives us, this is what the parsed dataset gives us for training data. As you can see, when we have two brackets, it means that we have an object. So this is an object from here to here, and this is an object from here to here, and it goes like this till the end. So here is the class map, and it has then the class, the label 0 for the class bathtub, and the label 1 for class Z. So here we normalize our training and testing data. We use the normalization between -1 and 1. And with this, the volume is not the K feature anymore. The algorithm should correlate other features and not the volume. So we then use this method in order to shuffle the training dataset. As you can see, it goes here. It's that. And we wanted to shuffle the training dataset in order to avoid the ordering of the data. So this is the architecture, the point net. Let's start from here. As you can see, we have the classification network here. It starts with an input in 3 dimensions, with n inputs in 3 dimensions. So we have to implement the number of points in 3 dimensions, and then to apply a t-net, each time we want to achieve an input transformation. So we then apply the convolutional network in 32 dimensions to simulate this part, the MLP part. And then apply again the t-net here to increase the number of dimensions again. And this process is continued until the number of dimensions reaches 500. So then to simulate the C part here, we apply a global max pooling layer. This is for the global features. And the D part, we apply 2 dense layers and the dropout layer. So the activation function that is used here is softmax. And as you can see, we have 2 classes. So the t-net, here is the code for t-net. As you can see, it has a convolutional layers, many convolutional layers that increases the dimensions of the input, and a global layer. Here you can see the dense, that means that our layers are fully connected. And also we have the orthogonal regularization, which we added this part here because we wanted our machine learning model to be deployed on a web page. So this is, you must put a get config function if you want to use your machine learning model on a web page. And then we have the convolutional layer that is made of conv1 to 1D layer and batch normalization with ReLU activation function. And dense layer with dense and batch normalization with ReLU activation function again. So in order to train our machine learning model, we use the method model.fit. So we use 20 epochs, as you can see here, and the training data. The validation data are the testing data. So This is the whole process that it goes on, and you can see that our accuracy is 98%. So the sparse categorical, it means that training and then involves passing data forward through the model and comparing predictions with ground truth labels. This is because this happens because this model, this neural network, is supervised. So sparse categorical checks if the maximal true value is equal to the index of the maximal predicted value. And the ball here, the ball value here, we can check the overfitting through this and also through the loss function, the value of the loss. If the metric of the testing data is staying the same or decreases while increasing on the training data set, it means that the overfitting of the model is happening. So the last library we used is TensorFlow.js, and we use it to convert and save our careless model in a file named myModel. So as you can see here, we have a file named myModel, and it contains a JSON and a bin file. So if you want to deploy your machine learning model, your pre-trained machine learning model on web, you have to use TensorFlow, load layers model, and import the JSON file, as we said before. So this outputs a prediction in matrices. So you need to, if you want your model to predict something, you need to use this function, this method, model.predict, which model is this. So this outputs numbers. If, for example, the number of your training data, the classes of your training data are 10, and the PR value is 3, that means that your training data might be an arbitrary, like for example here. That was all. Thank you very much.
Okay. Now we can see a little bit of the website. I gave you the link. Okay, here it is. So if you visit the website, you can see a poster paper we have to present in this conference. The most important is that you can download all the source code, okay? And for each one of the cases, you may get the data set that we were using for training and testing the algorithms. Now, if you pick one of the examples, let's see, for example, scene 1. You know, it needs some time to load the X3D model, and this is because, as you will see in the bottom, we were testing with 3 different levels of detail, 3 different numbers of vertices, but in order to not to upload 3 different models, we did something else. I mean, we are uploading the highest density, the most points, the biggest file, and then we are using, you know, in a random way, points from this one in order to test also how the algorithm reacts with less points than the highest. Okay, so it needs some time to upload. After that, Okay, you are creating the bounding box. Bounding boxes are very important because we need to separate. Look, here we have a scene. We don't have a model in order to make our algorithm running and you know, guessing which type of model is this. So we have first of all to split the scene, the whole scene into models. So we are doing that by using, of course, the structure of X3D. We all know, I mean, we are familiar with the structure of X3D. And by that way, we are splitting the scene into models, individual models. Okay, so we are creating the bounding boxes. It takes, as you can see, zero time to do it. Okay, we know that. Also, everywhere we put some splash screen in order to give you the how much time it was necessary for the running of each one of the individuals procedures. Okay, then we display bounding boxes. Okay, you can see that. Okay, so we know that we have several items there. I mean, we have walls, we have a sofa, we have chairs, we have tables, and some other individual things. Okay, and then we are running the neural network. As Chrysa said before, the neural network is already trained. We are not training now. The neural network is already trained, and now we are using in a JSON file the structure of the neural network, okay, and also the values of the weights. I mean the training weights, the trained weights. Okay, so in this case, let's say that our neural network is not going to retrain or something like that. I mean, we're not going to benefit from the tests in order to increase the training quality, but it is extremely very fast, as you will see. So you will see that okay, in a scene with 6, 7 objects, we will need very you know, less than 1 millisecond to get our results. Okay, it requires more time. Okay, it requires more time, you know, to make the let's say the screening. I mean the monitoring of the data than to calculate the results. So all this, in the end, of course, you may find here a link where you can download the dataset. Now, about the dataset, you may use it. It is of course the official ModelNet 40 dataset. Okay, but also we have enhanced this dataset especially for the testing. For the testing of the algorithm, we enhance it with several models that are outside the dataset. And this is because we would like to test how it reacts, the neural network mostly, how it reacts when you will feed it with some data that are outside the dataset. So that is all about the demo website we prepare for the tutorial and for the conference. Do you have anything else to say? I don't know, Jose, if you think it is necessary to say anything else.
No, I think we are okay.
Okay.
Are there any questions?
Yeah, let me check with the audience, and let's also have a look on the
chat window to see if someone connected had any question?
We had some discussion in the chat.
Yeah, there are some questions in the room.
Okay.
I will.
Clean it performance. Performance.
Could you use the same process to, for example, if you had models of 3D body scanning and say, I want to find armpits or I want to find the space between the legs and just narrow it down to actually get within a bounding box or within a zone and not just do tables and chairs and kind of soft objects as well?
If I hear well, because you know, I couldn't hear very clearly. I guess that you are asking if we test it with other kind of models except of the model 40, because these chairs and etc. are things that they are part of the data set. So we have to work with the data set, and the data set is full of that kind of models. Of course, also the, let's say, outside the out of the data set models we test, the algorithms, they were of the same kind, I'm afraid, because we had to be consistent to the indexes of the data set models. So we unfortunately we didn't test it right now with anything else.
My question is, could you expand this technique to include other types of data sets and models, for example?
Yes, yes. We believe that this technique can work very well. Although in the literature, to be honest, you won't find many things outside the ModelNet test bed, you know, and the outside the ModelNet that data set, because in general we are trying to use this kind of data set, but we are very, you know, in goodwill if we have a new data set, I mean, with other things as well, like for example humans or human organs or many other things from medicine or I don't know. We would like to test it, and we are offering, you know, if there is any other data set to help, you know, in this case.
And we should add that you would need labeled data set. It's not enough only to scan bodies, but you also have to segment parts and label each part with the right label. So I suppose that the answer is the model can learn some other forms other than chairs and tables. But for doing that, you really have to have huge amount of data of that kind. That is already there.
How huge of a data set? I mean, if I had 130 some scans, would that be enough to be able to say this is a leg, this is an arm, this is a head? Or do I need 1,000 things before it says, oh, I know what a head is on a human being?
I'm sorry, but I couldn't hear very well.
Let me try to say it again. So the question was how big the database should be. So going back to that example of human body, parts of human bodies, is about, let's say, 100 legs, or is about 1,000 or 10,000 legs?
Yeah. We need, in order to have let's say, a reliable training, we need a data set that it is 1,000 plus data models in this case. Okay. So we need quite, you know, quite good data set. But mainly, these algorithms are, let's say, in the literature, you will find a certain data set testings because of, algorithm evaluation reasons, mostly. But I am sure that the algorithms may work very well, no matter what the data set would be. And this is because of the way that they work. I mean, how the algorithms are structured. And so, as you can see, for example, in the case of PointNet, I mean, in the case of the algorithm that works with mostly with point clouds instead of meshes, you will see that the algorithm extracts critical points. Critical points means skeletal, let's say, points for each one of the individual models. So I am very confident that this, if we apply this to other data sets, it will work very well, because it is the way that it works that extracts edges, extracts skeletal information. So I don't think we will have problems. Also, anyway, Model 40 has some a quite interesting, good, let's say, variation of models. There are some human bodies, there are some, but okay, in our examples, we focus on chairs and tables and etc. because it was easier for us to do it in X3D, I mean in X3D environment. So it was not that easy to insert more complex scenes in the scene, models in the scene. But for example, it is interesting to understand how it specifies whether something is a chair and not a table, because more or less they have common, structure. So I am confident that it will work with no matter the data set would be. Okay, I don't know if I understood very well your question, I think.
Yeah, I think the answer was clear.
Mm-hmm.
Okay, let me see if we have some other questions from the room. One question from me: is the algorithm dependent on the tessellation level? If it's about mesh, did you observe that if you remesh an object, let's say with more triangles or less triangles, it has an impact on the result?
Yes. The story is vice versa. I mean, it's totally on the other side. I mean, we're not focusing on meshes, we're focusing on points. So instead of dealing with meshes, we increase the number of points, and we do it on the fly. Okay, so on the fly, we are starting from the 9,000 points model you saw in the example, and on the fly we increase this points. Okay, on the fly means with JavaScript inside the web page. Okay, and all of this were done, in real time, as I show you. So in real time we are increasing by triangulation the points. Okay, and we have a better prediction in this way. So we don't have to deal with meshes now. We may stay in points. Points are safer because, for example, as I said in the beginning, in the future, that's what I believe anyway. In the future services, we will deal with scanned 3D models mostly. I mean, our cars will have a laser scanner on top and scan everything. So our job is to get these scans, to make annotations on these scans, to classify the models, to segmentation, to make segmentation in the models. So it's better to do all these things, not to meshes, but to points. Because as you know, and we all know that, to go from points to meshes needs an extra effort, but sometimes needs also, human to react. So let's stay in points and do whatever we can do endpoints. Also, I may say as well that X3D support point clouds very well. Okay, so I think in the future we will have some more stuff to present in next year, Web3D perhaps, I hope, on segmentation as well, because right now me and Chrysa and other colleagues, we are working with segmentation also, and not only classification, because we think that we have many things to do as well there. Okay.
Okay, good, thank you. Other questions from the floor? No? No one from online?
Yeah, okay.
Yeah, if you want to add something more, we still have some time.
No, it's okay. We have the presentation Friday morning as well. So I want to thank you for attending the tutorial. I hope that I give you the first step in order to start working with deep learning and X3D as well. And see you around, I say. Okay,
Yeah.
Marius?
Yeah, thank you very much.
It was
See
really
you
nice.
Friday for your poster. Thank you.
Okay.
Thank you. So we are now taking a coffee break here, and let me show the screen with the program. Okay, so we are here in the schedule. We did this part. Yeah, we have some more time, extra time. So let's have a break, coffee plus and something else. And we will be here in the same room at 4, from 4 to 8 on a workshop on Web3D technologies for the Notre-Dame reconstruction project. Okay, I will keep the session open for the online people. So just be back in about 50 minutes. See you soon.
Violette? Ok. Ouais. Ouais, c'est bon.
Salut Violette, tu m'entends? Oui, mais moi je ne t'entends pas. Attends, je ne sais pas pourquoi. C'est dans...
Elle a coupé son micro.
Ah, ton micro est coupé, Violette.
Ouais,
Là, c'est
mais
bon?
non, ça doit fonctionner.
Vous m'entendez?
Maintenant, ça doit être mieux, mais... Oui, dis quelque chose. Ah, je sais pourquoi. Ah oui, c'est bon, je
C'est tout
t'entends.
bon?
Oui, très bien. Justement, on voulait vérifier que tu peux partager ton écran et tu essayes juste faire un test.
Oui, alors attendez. Là, c'est bon?
Encore, je vois pas encore l'écran. Non, toujours pas. En fait, je vois la caméra, mais pas l'écran, pas l'écran de l'ordinateur.
Ah, alors attendez. Qu'est-ce que c'est? Je peux réessayer. Là, vous voyez quelque chose?
Toujours la caméra. Il y a le cadre rouge qui s'est allumé?
Oui, oui.
D'accord, bizarre ça. Alors, est-ce que c'est moi qui ne vois pas la chose parce que j'ai une autre vue? C'est possible ça aussi. Zied, tu vois quoi, toi? Tu te connais? Tu vois la même chose que moi ou tu vois... Non. Non, on voit pas. Violette, l'écran partagé, on le voit pas.
Je sais pas trop quoi vous dire. Est-ce que je dois essayer de redémarrer?
Peut-être choisir une autre configuration de l'écran partagé, si c'est l'écran entier ou une application, jouons un peu sur ça.
Ok. Voilà.
Sur aussi Athanasios, parce qu'il n'a pas besoin d'être là. Violette, lors de workshop, d'autres personnes doivent partager aussi leur écran ou...
Oui.
Oui, d'autres personnes vont partager aussi l'écran. Il va falloir nous dire qui. Je suppose qu'il y a Roxane, parce que c'est de chez vous, non?
Roxane, Marco
Marco, oui, je le vois.
et Anaïs.
Anaïs, je ne la vois pas encore
Je ne peux
connectée.
pas encore être connectée.
Roxane, Marco et Anaïs.
Alors, attendez, je vais tenter de changer de configuration. On va essayer autrement. Si je fais ça comme ceci.
Et Marco?
Est-ce que là, vous voyez quelque chose?
Non, c'est la même chose. Essayons avec Marco ou Roxane, juste pour voir s'il y a... Hi Marco, I don't know if you speak French or English.
Hi there.
Yeah, let's do it in English. Marco, can you just try to share your screen? Because we cannot see Violette.
Absolutely.
Yeah, we can hear your screen. So it works for Marco. And then let's do the same for Roxane, if you can hear us.
Yes, I can try.
No, not coming.
apparently I have to authorize in my security preferences, so I'm just gonna do that and see if it works.
And Violette, in the meantime, maybe you can disconnect and connect again.
Oui. Ok, j'essaye.
Okay. Okay, we see you again, Violette.
Nouvelle tentative.
And we see your screen with the mountain, the one with the mountain. I don't know if there are several, but yeah, and the presentation now. Yeah, great.
Nice.
Good. So let's go back to Roxanne to be sure that she can also share the screen. So we see two Roxannes. Okay, now I think I got it. So we have twice, Roxanne, we have you twice, but only with one account you are in a presenter mode. So maybe we need to also give to the other account. You also have a phone, or just a second. Ziad, la deux Roxane, mais aussi l'autre Roxane en invité. Quite easy to duplicate in virtual. We have two Roxanes.
On t'entend pas, Roxane?
Yeah, and now you.
Yeah.
Okay.
Okay, so yeah, I don't know why I was appearing twice. I had to restart Google to allow to share my screen, but so let's see.
Yeah, I see myself, so it means that I see your screen.
Yeah, okay, perfect.
Good. So we have Mark, Roxanne, and Violette.
Yeah.
You all three can share your screen, and the fourth one is Anais, but she's not yet here now. When she will arrive, we will do the test with her also. Yeah. We still have 5 minutes, so it's okay. So the last coffee, and we will come back.
Bon, je lui ai renvoyé le lien au cas où. Ciao, Marco.
Hi, everyone.
Come stai?
So, which is the speaking order? So you will do the
Roxane, est-ce que tu as le numéro d'Anaïs?
Non, mais elle est sur le groupe WhatsApp. Je peux éventuellement mettre un truc si tu veux.
Éventuellement, si tu peux lui écrire pour lui demander si tout va bien.
Ho guardato il video Paolo e ti dico, ma te mi ci fai
Hello again. Do we have Anaïs?
No.
She will be the first or the second, or she will come later?
No.
If she's not the first, it's fine. Then if you can start, when she is arriving, we just give her the presenter rights, and that will work. Ah, she's here. Okay. Hello, Anaïs. Good. So, Ziad, can you add also Anaïs in the list of? Okay. So let's wait 2 more minutes for people from the coffee break to come. You compete against the coffee, so you have strong competition. There are also some macarons, so maybe that's
the coffee is winning.
Always. Okay, and also let's see how many people are connected. We have 11. Okay, let's also wait them. Hello, done. Good to see that the sun also came on your side this morning. Yeah, good. Okay, I think that we should start. Let me just make sure that people here can see you. Just a second. Okay. Be sure that you are projected on the big screen. Okay, it is good that you have the microphone cut, all of you, but only the speaker that will use it. Okay, and then if I cut mine. Oh, so I suppose that you couldn't hear me. Okay, good. Okay, so let's start our second workshop in at least in this room. So we have a team of 4. Initially was set to be a team of 5, but unfortunately Livio had some personal problems and he couldn't join us. But I'm pretty sure that the team we have here can replace him very well. So Anaïs, you have the floor to start the workshop and run the show. Oh, not Anaïs, so sorry, Violette. Yeah.
Thank you. Is it okay? Do you see my screen?
Perfectly.
Okay, nice. Thank you very much. Hello, everybody. First of all, I would like to thank the organizers for this event and also for suggesting this session on the Notre-Dame Scientific Action. As you can see, I'm not Livio de Luca. Unfortunately, he could not come due to personal problems. And we are really sorry for this last-minute change. So, my name is Violette Abergel. I'm a researcher at the MAP laboratory, which is based in Marseille, in France. And as my colleagues here, I'm involved in the Digital Data Working Group, which is coordinated by Livio. So today I try to take his shoes, or at least I try to do so, but Livio is coordinator, we are not, so maybe we'll have some specific or broad questions about the worksite that we won't be able to answer as precisely as he would have, but be sure we will do our best. Now, I think it's time to introduce my colleagues and give an overview of the program for this session. Of course, Roxane, Marco, Anaïs, please feel free to present you in more detail just after that or in the beginning of your presentation as you like. So I will start with an introduction initially made by Livio to present the role of the Digital Data Working Group in the general scientific action and its ambitions regarding the construction of a digital ecosystem. Then Roxane Roussel, which is a studio engineer at the MAP laboratory and which works on the semantic enrichment of digital data collected during the restoration project, will present an approach to build a complete digital report of the cathedral after fire with the IOLI platform. And then we have the pleasure to welcome Marco Calieri, who is a senior researcher at the Visual Computing Lab of ISTE. He's the main architect of the 3D of web-based visualization and analysis application, and today he will present its use in the specific context of the study of ripstones. And then we will listen to Anaïs Guilhem, who is a researcher at the Laboratoire de Recherche des Monuments Historiques, and she will present the results of a collaborative work on the digital physical anastylosis of the nave arc. And finally, I leave Livio's shoes to present my work within the working group, and it concerns the visualization and exploration of semantically enriched data. And then, of course, we will keep a moment for discussion and to answer your questions if you have some. So now, Roxane, Marco, Anaïs, am I missing something, or do you want to say a word before we start? No?
No, perfect.
Okay, so then we can start. So, as you know, the fire hit Notre-Dame de Paris more than 3 years ago, opening obviously a new page on its long history. And beyond the painful nature of this moment, this accident really soon gave rise to a kind of national impulse, in particular among all the communities interested in cultural heritage, uniting by this way many actors from different disciplines that were willing to put their knowledge or their skills at the service of the study of the cathedral and its restoration. And the setting up of this collective work quickly revealed some challenges, which concerns, for example, the recovery of knowledge about the materials and architectural elements before the fire, or also the extraction of information from the spared materials to better understand those that were affected by the fire, the study of climate evolution through physico-chemical analysis, the coupling of different modeling systems to perform geometric and structural and acoustic studies or simulations, and even the study of the emotions that were aroused by this common heritage through different strategies of capture or analysis. But at the same time, to be honest, we also have to consider this as an opportunity, because these work sites also bring a quite privileged framework, not only to study the cathedral in all its dimensions, down to the materials and technical details and in all its temporalities, but also for taking a step back and observing the collective analysis and interpretation of facts, of objects and phenomena that brings together the production of data and knowledge towards the construction of collective resources around the very same cultural heritage objects. So, quickly after the fire, the CNRS and the Ministry of Culture set up a scientific work site to coordinate all the scientific actions around the cathedral. And as I said, it's a large research topic, and the project has mainly two aims. Of course, to provide useful information for the restoration work, but also to benefit from this unique opportunity to renew our knowledge of the building, of its architecture, its history, its environment, and so on. So it's important to note that the scientific worksite is not the same thing as the restoration worksite. Obviously, the two feed into each other, but do not have the same goals and the same time frames. So this project brings together more than 175 people from more than 50 laboratories, which are divided into 9 thematic groups. The Digital Data Working Group, coordinated by Livio de Luca, brings together about 30 people from 12 research units and 2 consortia. And this working group is a bit particular because it defines itself as, let's say, an interface between all the other groups, because everyone produces digital data, and one of our purposes is to facilitate the exchanges between all the researchers and restoration actors. The underlying hypothesis of our work is that in a context where the data produced are at the same time abundant, multidimensional, and highly heterogeneous, digital technology is certainly a key for highlighting the mechanisms of knowledge production specific to each discipline, to each research group, or even to each person involved in the study of complex objects such as Notre-Dame. But without going into too much detail, there are obviously still gaps to be overcome, where we are seeking to concentrate our efforts. So the first one is a semantic gap, because if today we are witnessing a massive but scattered production of digital resources of cultural heritage objects, this growing mass of uninterpreted data clearly shows a need for innovative methods to move towards a centralized mass production of semantically enriched digital resources within multidisciplinary research perspectives. And the second one is a memory gap, because even though knowledge engineering approaches introduce many solutions for aggregating, implementing, or investigating the evolution of data, all these approaches still remain quite difficult to apply in an effective way in our specific context of cultural heritage science, because it's a domain where workflows involve a long tail of subjective human decisions, of non-explicit research protocols or poorly formalized knowledge, and even highly individualized skills. So for us, it becomes really essential to understand how we can memorize these processes and also make them comparable with each other. And the third one is the correlation gap. Here again, some works provide methodological frameworks for aggregating multi-thematic observations and even for spatializing together highly heterogeneous data. In particular, IOLI, that we will present just after, allows to aggregate multi-thematic observations around the semantically structured 3D representation of a cultural heritage object. But now the major issue is to build autonomous mechanisms that will be able to build new interconnections between all these collected resources, be it semantic or formal, visual, temporal, whatever. But with this final aim to allow the exploration of completely new informational spaces that would be based on the exploitation of these relationships. And the last one is the technological gap, because works on 3D annotation, signal processing, or from the field of knowledge modeling can, yes, be mobilized to automatically search datasets of different types, production modes, or processing stages all along their relationships. But we can say that the effective potential of all these isolated contributions in digital methods and tools would need to make them converge into systemic integration and experimentation frameworks. And of course, it also raises some methodological questions. So I won't spend so much time on abstract considerations, but if I had to sum up the ambitions of the Digital Data Working Group, I would say that by overcoming these four gaps, it would be the idea to build a digital ecosystem allowing to link physical features and collective knowledge through digital 3D representations. And also to consider the spatialization as a big opportunity to memorize the pathways that start from scientific questions and lead to data and knowledge production. And in fine, so at the end, to be able to analyze in a transversal way some links between material objects of the work sites and the object of knowledge we have aggregated and formalized through the exploration of the relationships linking data or concepts together. But in the first instance, the actions of the Digital Data Working Group have prioritized urgent needs for the reconstruction of the cathedral, in particular by providing dedicated methods and tools to acquire 3D data. I'll give an example later. To compare different temporal states of the cathedral before and after the fire. So in this example, you can see the comparison of the vaults before and after the fire, showing how the fire caused structural changes that must be taken into account for the very first works on the cathedral, where it was about stabilizing the monument before even thinking about the ways to restore it. And also some methods to carry out in 3D the architectural diagnosis on which the restoration work would be based, and contextualize all the observations made concerning Notre-Dame's condition. But Roxane will explain all that later. And also to propose a restitution hypothesis in anticipation of the identical reconstruction of the monument, for example, of the burnt roof structure here, or also of the collapsed transverse arch in the nave, but here again, we will come back to this later. And at the same time, we quickly started to set up a kind of technological bricks to meet the need of the scientific worksite and the restoration worksite, allowing to collect all the data produced on the cathedral, to document it, to semantically annotate it, and to spatialize it and visualize it. And this framework constitutes the very basis of our ecosystem, and all these software elements are based on web technologies. They are all coming from research laboratories, and most of all, they are all interconnected to each other through web services or API. So, for example, ArcheoGrid here can properly communicate directly with OpenTeso or with the viewer without any problem. And we called all this technological framework the NDAM platform. So far, we collected more than 180,000 pictures, several thousands of 3D point clouds, hundreds of technical drawings, several hundreds of documentary sources relating to Notre-Dame's history. But the members of the work site also produced many data, like bibliography, material analysis, technical surveys, drawings, acoustic samples, mechanical simulations, interviews, citizen surveys, and so on. So, to give a quick overview of our actions, here are the 4 main areas of our activities. As I mentioned, the first one concerns the production modality of modalities of on-site and in-lab ready-to-enrich data. That's to say, to propose some methods and tools suited to the specificities of the worksite to acquire data, to store data, and to document data fluently, keeping track of the processes that led to its creation. For example, here you can see a 3D digitization device developed to digitize really quickly the remains collected during excavations, such as the ripstones. And the tool you can see here in bottom left is a 3D-Op, a software brick of our ecosystem, which was used to analyze the ripstones, their typologies, the tools marks left by the stone carvers, and so on. And Marco will detail these experiments about it in its presentation. And here you can see an illustration of an experiment that aims to integrate metadata directly into the files resulting from this digitization process, which not only makes the documentation pipeline more fluid and versatile, but also ensures that the existence of the metadata remains intrinsically linked to the files they inform and not constrained by the use of one software or another. And here you can see one of another software brick I mentioned before. It's ArcheoGrid. It's a web platform dedicated to data indexation, allowing to manage descriptive sheets, be it based on standards like Dublin Core or custom descriptive models. And it also allows to filter or find resources in all the collected dataset. And the second area of our actions concerns the spatio-temporal distribution of data stream. Here you have an interesting example of this need to propose custom methods suited to the specificities of the worksite, because here, okay, as you know, during the fire, the roof structure burnt and many remains fell on the walls. And to assist the sorting and to keep track of the position of all these elements before their removal, the working group was asked to digitize it in 3D. But the place is really tight and only accessible to climbers. So the particular configuration of the site made it really difficult to use laser scanners and did not allow at all the use of drones as we do usually. And to solve this problem, a researcher of the working group proposed to design a custom-made device to perform some photogrammetric acquisitions. So actually, it's a kind of a cable cam. So that's to say, here a mount with 3 cameras fixed on a device which slides along a cable stretched across the nave. And an upstream simulation in 3D was used to optimize the positioning of the cables and all the camera's parameters to ensure sufficient coverage while optimizing the deployment time, which obviously had to have as little impact as possible on the worksite activities. And here on the bottom left, you can see a resulting 3D point cloud. So as you can see, it's quite dense with a resolution, I think, around 3 millimeters. With the project Repérage, one of our actions were to propose a methodology to proceed to the spatio-temporal distribution of artifacts. Here again, it was ripstones. I won't spend so much time on this topic that Livio would had explained much better than I could. But here the idea is to use photogrammetric pipeline and similarities measurements inside a big corpus of images to find the localization of the ripstones before and after the fire. I think maybe Anaïs will talk about the project later. And with all these works, we are able to constitute a corpus of spatialized and multidimensional and highly heterogeneous digital data corpus. So here a challenge is to allow the web visualization and exploitation so that basically every actor of the scientific or restoration worksite can explore the corpus in 3D, can perform some comparisons and so on. But it's the topic of my presentation, so I won't elaborate now. We'll see at the end of the session. And it's one thing to be able to collect and visualize spatialized data, but it's another to be able to semantically enrich them. That it's clearly it's the aim of this third activity area. So this work relies on a web platform we are developing for many years at the MAP laboratory, which is dedicated to collaborative 2D, 3D annotation for documentation of cultural heritage. Here, the principle of Aioli's platform is based on the spatialization of images by photogrammetry. So basically, the user would create a project from a simple set of pictures of his study object. And these pictures are used to build the point cloud of the objects, like here. And thanks to the memorization of the projective relationships between the point clouds and the images, from this moment, the user can annotate any image of the project by drawing a region on it. And this annotation will be automatically reprojected on the point cloud, but also on all the other images on the datasets on which the area is visible. And at the same time, the annotation propagation process performs some calculation to compute 3D descriptors like normals, roughness, curvature, and so on, that will complete the semantic description made by the owner of the project or by his collaborators. Obviously, the description sheets linked to the annotation are totally flexible, so the user is completely free to choose the structure that fit his needs. For example, to choose that all the annotation of the degradation layer must mention a text field to describe the observation and a date to specify the date of the observation, or whatever. Roxane will show you the tool in action, so maybe it will be more meaningful. But basically, Aioli has been used to carry out some projects transcribing the diagnosis made by the architects in charge of the restoration. And as you will see just after, it's a big piece of work that led to several hundreds of 3D annotations. Okay, so here you can see some annotations of the remains of the rough structure. They are all spatialized in 3D. And the short-term perspective would be to extend this principle to other spatialized representations, in particular to hypothetical restitutions, always using the potential of geometrical reprojection based on the prior spatialization of all the corpus resources. Like here, the 3D restitution of the rough structure, I think it would be an excellent candidate to track some wood remains or to document various attributes, for example, regarding an archaeological point of view, or structure typologies, or material samples, and so on.